Hello, class. Welcome to chapter 3. So we will, in this chapter, discuss quadratic equations, quadratic functions. And to get ready for that, we have to discuss something we call complex numbers, as we will encounter those soon enough. So it turns out that the real numbers that we discussed first day of classes is not the biggest set of numbers out there. In fact, there is a larger set of numbers that have been discovered after the real numbers have been completed, let's just say. We figured out there were whole numbers, there are integers, there are rational numbers, they're actually irrational numbers. And so then that set of numbers got completed, and we said, okay, these are all the numbers, we're going to call them real numbers. And then we found some more, okay? So then we had to include those to the set of real numbers and say, okay, the new set of numbers, the reals and the non-reals, are going to be called complex. So that's what a complex number system is. It's an extended number system that includes the real numbers as a subset. And then there's more. So what's more is that we discovered that actually we can have negative numbers inside a square root. And so, of course, we discussed that there is no real number that multiplied to itself would get you a -1. So therefore, the square root of -1 is not real, so does not exist, but it simply does not exist in the real number systems, okay? However, it is a number, and therefore we had to extend this set of numbers, and we call this square root of -1 by I. It's not 1, it's not 2, it's not x, it's the number I. And I stands in for the imaginary unit. Same as 1 is the real unit. Remember how we talked about the real number line? We said here is 0, then pick yourself a unit of measure, right? Pick yourself the 1. And then based on this 1, you can build up your real numbers, yes? So 1 is the real unit, or the unit for the real numbers. I is the imaginary unit on which all the imaginary numbers are going to get built up. Now, as you see from this equation here, we call I, so the square root of -1, the answer for it is I, the imaginary unit. However, if we square both sides of this equation, squaring would get rid of the square root symbol. And so, as you see, I squared is back a real number, and it equals to -1. So this imaginary number, when you square it, you get back the real number, -1. So just as the definition of the square root says, what number multiplied to itself twice, in other words, squared, would equal to -1, that number is I. Okay. All right, so what we need to discuss next is how do we deal with these complex numbers? In other words, really, how do we add, subtract, multiply, and divide complex numbers? It's really simple. What you need to, though, keep in mind at all times is that I squared has the value of -1, and as such, it should be replaced to it. So for now, a complex number is simply a number that looks of the form a plus bi, where a and b are real numbers. So in other words, a complex number, for example, might look like 2 plus 3i. So a complex number is made up of a real part. So it has two real parts. It really has two ones. And it has 3 imaginary parts. In other words, it has 3 eyes. So this complex, just as the name suggests, is made up of several layers. It's made up of 2 real parts, so 2 ones, and 3 imaginary parts, so 3 eyes. So again, if you look at it, for example, the number 5i, then the real part is 0. So it has no ones, right? It has 0 real parts. And it has 5 imaginary parts. We call a number like this that only has imaginary parts and not real parts pure imaginary. And so by the same token, the number 4 has 4 real parts and 0 imaginary parts. So we call this number pure real or simply a real number. Right? So a real number is a complex number with no imaginary part to it. Okay, just only made up of real parts. All right, so that's what a complex number looks like. It could have an imaginary part to it. It doesn't have to be. But complex numbers are numbers that are made up of reals and imaginary, or either one of those parts can be missing. Okay, so let's see where complex numbers come from. Here it is, the square root of -9. I'm going to rewrite this to you as -1 times 9 because that's what -9 equals to. So if you take this apart, that's the same as the square root of -9 times this -1 times the square root of 9. And then the square root of -1 is equal to I, and the square root of 9 is 3. But this number's, of course, is I times 3, but it looks better if you write the number up front. So 3I. Okay, so if you take 3i and multiply it to 3i, you're going to get -9. Let's try this again. Same thing. I'm going to take the square root of 24 and look at it as a -1 times the square root of 24. So this square root of -1 equals to I. And then the square root of 24, you can leave it up as it is. This is a times. You can leave the square root of 24 as it is. You may take your calculators that can simplify radicals. You hopefully might remember something from your other algebra classes that say to simplify radicals, you have to think on whether or not you have perfect square factors inside. So same as the -1 came as an I, the 4 factor of the square root of 24 can be simplified as a 2, and then the 6 is the only thing left inside the square root. Now, if this freaks you out, don't worry. You may leave the answer simply as a I times the square root of 24. You don't need to simplify the radical parts. That's not really as much or as important as recognizing the fact that you're dealing with a complex number, and therefore that negative number inside the square root has to make its way out as an I. Here is one more. Again, the square root of -16. -16 is a -1 times a +16. I can write it out if you want. But again, the square root of -1, that has the value I, right? That's what the square root of -1 is named I. And the square root of 16, that has a perfect exact value of 4. And same thing as we did before. In this case, kind of like we don't write I x2, but rather 2x. It's a multiplication, but we like the order of these two factors to be numerical one first, and then the variable. Well, it's not a variable, but then the I, the letter. The reason why I'm leaving this I here at the front, kind of tucked in the middle, it's the same thing as 2 square root of 6i. But we never ever like to write anything behind square roots because then it's, some of you might make the square root shorter, longer, and then we're never sure, is this value inside the square root or is it outside the square root? So no matter what, we don't like to write numbers behind or anything behind a square root. Possible, write them in the front. But it's not wrong to say 2 squared of 6i if it's clear that that I is on the outside. So as a matter of fact, when I was in school, we learned to make square root symbols have a little extra dip at the back to show that's where it ends. So then if I write something behind it, whatever it is, then I know that's outside because it's written after the little extra dip. All right. So here it is. How do we add, subtract, multiply, and divide complex numbers? It's extremely easy. It's just like you would combine like terms. So to subtract, I'm going to change the signs of everything that follows. So in other words, I'm distributing in the minus. And then it's just like combining like terms. Add the real parts together, add the imaginary parts together, and that's it. This problem here is even easier because it's a plus up front, so there's nothing to distribute. So 5 plus 8 is 13. 3i plus 2, I'm sorry, I messed it up. That's a minus. So negative 3i plus 2i is negative 1i. You can write the 1 if you want, or you can write it without the 1. We know it means 1i. So before we get on adding these two complex numbers, we're going to simplify these radicals and tell what they mean. So here it is. The square root of negative 25, and again, you don't need to write all these steps, but if it helps for now, you should. As in, maybe you already know the minus comes out as an I. And the square root of 25 is just a 5. Same thing, the minus inside the square root, that means the I, imaginary unit. And the square root of 16 is just the 4. And now when I add these complex numbers, add the real parts. And then add the imaginary parts. So same thing, negative 5 plus 4 equals to negative 1i. So what's definitely way more interesting is multiplying complex numbers. So let me show you. The first one is easy. All I'm going to do is obviously just distribute in the 4. So it very much looks just like that I might be an X, but it's not really a variable. It's a letter, but it doesn't stand in for an unknown quantity. That letter stands in for the value of the square root of negative 1. Okay. However, this is it. That's the answer. Nothing more we can do. There are no like terms, so no real parts to be added together, right? Imaginary parts to be added together. So let's distribute this one here. So I'm going to get 4 times 2 is 8. 4 times negative 5i is negative 20i. 3i times 2 is 6i. And here it is, negative 15. I times I is an I squared. And here is where the difference very much between an x and an I is. X squared is just that. We don't know the value of x. However, I squared has a value. What is the value of I squared? Right here from the beginning, since the value of I is the square root of negative 1, when we square both sides, and I mentioned that at the time, that is very important to recognize that I squared equals to negative 1, and therefore it must be substituted with it anytime you see an I squared. So here it is. I squared should be replaced with a negative 1. And so when we replace it with a negative 1, negative 15 times negative 1, that switches over to a positive 15. Okay. So again, I squared has the value of negative 1, and therefore I multiply the negative 15 up front to negative 1. So that's going to get me then a 23, because that's what 8 plus 15 is, minus 14i. And again, combine like terms once you have the I squared. So that's, again, what's going to happen. That's the difference to multiplying i's versus just adding them. You will end up with an I squared that has to be replaced. So here it is one more time. I'm going to simplify these expressions. So the square root of negative 16 is the positive 4i that we simplified several times. This has to be multiplied to 5 plus, again, the square root of negative 36. The negative 1 comes out as an I, and the square root of 36, put in your calculator, has a value of 6. So that's 6i. Okay. All right. And now we're going to distribute just this up above. So 15 plus 18i minus 20i and minus 24, and here is your I squared. And so because I squared equals to negative 1, negative 24 times negative 1 equals to a positive 24. So let me take this back here. Combining like terms, that's going to get me a 39 minus 2i. Okay. All right, so we're not going to practice more multiplication because it turns out to divide complex numbers, which is almost our last thing to do for this section, we multiply by the conjugate. So a division of complex numbers turns into multiplication. So here it is. The complex conjugate that's going to be important in future chapters is the one that you have if you switch. It's found by switching the sign or changing the sign of the imaginary part. Not everything. It's not the opposite. You just change the sign on the imaginary part. The real part is left unchanged. Okay. So to divide complex numbers, we multiply top and bottom by the complex conjugate of the denominator. So let's practice this and see what that means. So here it is. I'm going to write it again because I don't have much space. So to divide these two complex numbers, it says we're going to multiply top and bottom by the complex conjugate of the denominator. So multiply top and bottom by the complex conjugate of the denominator is just switch the sign on the imaginary part. So multiply by 4 plus I. Now, why top and bottom? Because we need to keep the fraction the same. Whatever you do to the numerator, you have to do to the denominator in order to keep the fraction the same value. So let's see what we get. At the top, I'm going to distribute the numerators. So 2 times 4 is 8, 2 times I is 2I, 5I times 4 is 20I, and 5I times I is 5I squared. Same thing at the bottom. 4 times 4 is 16, plus 4I, minus 4I, and minus I times I is an I squared. All right. Now, before we go on, we're going to change any I squared with a negative 1. You might as well combine the i's. You don't need to copy them all. It's 22 of them. But 5 times, again, I squared is a negative 1, so that changes that 5 to a negative 5. In the denominator, by the way, 4I minus 4I, that makes 0 i's, so really no I at all. And negative 1, that makes it a positive 1. So there I have at the numerator a 3 plus 22I, and at the bottom just the 17. So the reason why we did this switching is because, as you see, and it actually says here, when a complex number is multiplied by its complex conjugate, the result is a real number. Because what happens is these imaginary parts get to be canceled out because of the plus minus nature of what their coefficients are going to be. And because we only have now one number at the bottom, we get to distribute that one number to each of the terms at the top. So what I want you to notice before moving on and doing more problems is that it really doesn't matter what we actually ever do to a complex number. We will always get an answer that looks like another complex number. Again, what does a complex number look like? A plus BI. So you see a real part and an imaginary part. So it doesn't matter whether we add them, subtract them. Well, fine, the top was a subtraction. You see how you have an A plus BI for your answer? An A plus BI for your answer. We multiply them, switch the I squared to a negative 1, and there you go. The answer is an A plus BI form. So every single time we get a real part plus something imaginary. So that's exactly what we wanted here as well. Our answer is of the form A plus BI. So I could see the real part of the complex number and the imaginary part of the complex number. And so with this trick of switching the signs in the middle, well, we ended up doing just adding real numbers together. And therefore, we only had one term in the denominator that gets distributed or divided into each of the terms at the top. So let's try this a couple more times. So again, the complex conjugate of the denominator is 2 minus 3i. So that's what we get. Now let's distribute. So 7 times 2 is 14. 7 times negative 3i is negative 21i. 2i times 2 is 4i. And 2i times negative 3i is a negative 6i squared. The bottom, I'm going to get a 4 minus 6i plus 6i and minus 9i squared. Switch any I squares into a negative 1. It's negative 17i, and again, I squared equals to negative 1. Negative 1 times the negative 6 up front makes it a positive 6. These two guys are gone. They add up to 0 i's. And same thing, 9i squared The I squared's just switching the sign to the number at the front. So -9 times -1 equals to +9. So finishing up this problem, I'm going to get 20 minus 17i divided by 13, which equals to 20 over 13 minus 17 over 13i. This looks a little funny. Okay. All right, here's one more. This looks a little funny because you really have a 0 plus I here in the denominator. And the complex conjugate of 0 plus I is 0 minus I. Okay, you can write the 0 if you wish. But let's see what we get. So 1 times -I is -I. Negative 2i times -I is a positive 2i squared. And at the bottom, 1i times -1i is -1i squared. Again, I squared equals to -1, which switches the sign to a -2. I squared is a -1 times -1 is a +1. Look how nice. Dividing by 1 doesn't make any difference. And just so we can keep it real part first and then imaginary part second, then there's your answer. Okay, so remember what I said, that no matter what you will ever do to a complex number, the answer actually always reduces back to an a plus bi. So it will be a real part plus an imaginary part. So you'll never see an I squared because it equals to -1. You never see an I cubed, an I to the 4th, an I to the 372. It always reduces back to 1 or -1 and I or -I. So here are the powers of I. Of course, I to the power of 1, that's just I. We already know that I squared has the value of -1. However, what does I cube equal to? I cube is an I squared times another I, right? So the I squared part is a -1 times I. Well, there you go, -I. What is an I to the 4th equal to? An I to the 4th is really an I squared times an I squared. So that's a -1 times a -1, which equals to just a +1. I to the 5th is really right back because I to the 5th is an I to the 4th times one more I. What does I to the 4th equal to? 1. So I to the 5th is I. I to the 6th is I to the 4th times I squared, right? So it's a repeated multiplication. You can look at the first 4 I factors in that product as I to the 4th times 2 more i's, right, to get you to I to the 6th. But I to the 4th is 1. 1 times I squared is back to -1. And so the story goes. So really, what you have is that powers of I repeat every 4th. Okay, because they repeat every 4th, all we have to do is think about where in a multiple of 4 are we. So by the way, you can think of multiples of 4. So by the way, 18 is an 16 plus 2. I to the 16th is a multiple of 4. So it fits as a 1, right? So it's at the end, and then it's the same as the I squared. This is a 1. And so is the same as I squared, which equals to negative 1. I to the 35 is an I to the 32 is a multiple of 4. So it's the same as an I to the 32 times an I cubed. So that's the same as I to the third, which equals to negative I. I to the 44, 44 is already a multiple of 4. So it fits right here with every multiple of 4. Now, one way to do that is to really look at the remainder. So the remainder that is left after a multiple of 4 is the one that gives you the clue. So if you take 44 and divide by 4, you get a remainder of 0. So you are at a multiple of 4. If you take 35 and divide it by 4, the calculator might tell you 8 3/4 or 8.75. So you are at 3/4, right? Which means an I to the third. So that's 3 extra I's after a multiple of 4. These ones are a little tricky because I to the negative 20, again, I'm not really going to ask you these, is 1 over I to the 20. So make a positive, okay? And so I to the 20, 20 is a multiple of 4, so it fits exactly even. And there you have it. So that's a 1. And finally, I to the 13. 13 is an I to the 12 times 1 more I. Yes. And the I to the 12. 12 is a multiple of 4, so that's your 1. So it fits as a 1. And now I have the 1 over I, which is going back to the story we just discussed. To take 1 and divide it by I, since I is a complex number, I'm multiplying top and bottom by its complex conjugate. So I'm going to get a negative I, and I squared is a negative 1 times the negative at the front that makes it a positive 1. So that's a negative I. All right. Play with this is really not that important. I gave you a few in the homework to figure it out. You have to think about where in a multiple of 4 are you. 1 more, 2 more, 3 more, 4 more than a multiple of 4. It is a multiple of 4, so you're back at 1. Right? And that's our section about complex numbers.